All right, so to pick it up where we left off last time, we were transitioning into searching and sorting. And just to motivate this really quick, it's a huge part of computer science's data processing. So much so that we now have a completely different discipline, a completely different major now called data science, right? So a huge part of computing, I should say, is data processing. And the two fundamental operations to anything when you do data-wise is searching and sorting. In fact, these form the basis of a pre-processing step to many different algorithms. Usually, if you want to do something more complex, more sophisticated, the first step is to sort it so that you have it in some sort of order, or you need to find the needle in the haystack or something like that. There's also a large variety of different algorithms, different algorithmic strategies. For example, decrease and conquer and divide and conquer are two strategies that we already introduced so that you can, in the context of recursion, right? So last time we did this demonstration where we wrote a function to search a particular collection for a particular element. And what did that actually mean? Well, that meant an array for a particular integer, right? And so we had something that looked like this, right, where we took an array, a key, and then we iterated over it, and if we found it, then we returned the index at which we found it. Well, then we decided, well, what happens if we want to do this for doubles? Cut, paste, and repeat, except that you're just changing the type, right? What if we wanted to do this for strings? Cut, paste, repeat, but instead of the equality operator here, we had to use strcpy, or CMP, for string comparisons. And if we wanted to do something for, say, books, right? Book, or in this case, it's airport, I guess, right? Airport, right? If we wanted to search for that particular airport, Omaha's Epley Field, right? Then we would want to go through and search for that particular airport's GPS ID or name or whatever, right? You see me cutting and pasting, cutting and pasting, cutting and pasting. We're going to solve this problem today by writing one of these functions. Just a generic search function that searches any type of array. Not just an integer array, not just a double array, not just a string array, not just a airport array. All right? So we're going to get rid of all of those duplicates and we're going to winnow it down to one solution. Okay? So to do that though, what we're going to have to do is we're going to have to make this generic. Okay? And what that means is bringing in something new. All right, in fact, a couple of things that are new. The first thing that to motivate this, I don't want this. There we go. To motivate this, we're going to look at searching and sorting in practice. So again, in general, you don't even write your own searching and sorting algorithms. We will, but that's just to understand how they work. At the end of the day, we're going to use whatever's built into the language. For C, that means Q-sort, which is quicksort, and L-find, which is a linear search algorithm, and a B-search, which we'll cover later. Right? However, the built-in functionality is generic. It doesn't know what the things are. For example, if I have this thing that searches an array of what? Right? How do I know that that is the needle in the haystack that I'm searching? Right? You need to give it something else, and that something else is what we call a comparator. Right? So the basic strategy is as follows. We write generic algorithms, functions, right, that can take any type of array, all right? And it performs its basic search. It just iterates through, asking, is this it? No, is this it? No, is this it? Etc. You have to pass in another component to the function that is responsible for comparing elements. And that thing is called a comparator, right? Not a real word, at least I don't think it's a real word, but it's a real word in computer science. Right? So what is a comparator? Comparators in C, right? In C, a comparator is simply just a function, or a comparator function, right? And it has, we'll talk about the signature here in a second, but here's its basic functionality. It takes two elements, A and B. And note here, I'm not using code script here. I'm using mathematical script because we want to think about this a little bit more general. What are A and B? Are they integers? Are they doubles? Are they strings? Are they airports? Are they books? Yes, they can be any of those things. And so what is the comparator function going to do? It returns something, and here I'll emphasize that, something negative if A comes before B. A is strictly less than B. Right? It returns 0 if A is equal to B. And once again, I am using math notation there. That is not an assignment operation. That is now algebra. Right? If A and B are the same thing, right? It returns something positive if A is greater than B, right? Or alternatively, another way of putting this is that B comes before A, right? There we go. Now, we've seen this pattern before. strcmp does this, right? Given two strings, apple and banana, it will return something negative because apple comes before banana. Banana and apple, it will return something negative because banana comes after apple. They are out of order. But if I give it apple and apple, it will return 0. That's your way of testing whether or not two strings are the same. It's the same basic pattern. In fact, this pattern is invariant along any programming language. Every programming language will have something like this, where you use the built-in searching and sorting features of that language, but then you can provide some configuration using a comparator pattern like this. Right? In C specifically, a comparator function must have the following prototype. It returns an integer. The name is meaningless. CMP, or you give it a name that describes what it compares. And then it takes these two things. Two const void pointers. Right? So what are these? Right? First of all, there we go. First of all, it returns an integer as per the pattern above. Right? Something negative, negative, positive, or 0. Right? Do not assume anything about the actual value. In other words, negative could be negative 42. It could be negative 1. It could be negative 101. Right? All of those things are the same pattern. They're all negative. Right? Just like 0 is false and 1 is true, 2 is true, negative 2 is true. Right? Don't read anything into the magnitude of that number. Just understand that it's positive, negative, or 0. Right? It takes two generic void pointers. Right? And why does it do that? It allows you to compare any type of values, right? Because it's a generic void pointer. It's just a raw memory location. Now, where have we seen generic void pointers before? Const void star, or not const void star, but void star. Do we remember? So we use malloc all the time, right? What does malloc return? A generic void pointer. Just a raw memory location. You want space enough for 5 integers. There's not a malloc for integers. There's not a malloc for doubles. There's not a malloc for strings. There's not a malloc for airports, right? Instead, there is just one malloc. What does it return? It returns void star, so that you don't have a million different functions that all do the same thing. There's just one, right? So that can point to any type of value, right? Here we go. Inside the function, you follow the following pattern. So number 1, you cast the generic void pointers as the type that you expect, right? An integer, an int, a double, or an airport if you want, right? Once you've got that, you can then use the state of the object. You can use the state or value of the type and determine the relative ordering. Return something negative, or something negative, positive, or 0, depending on how you want to order those things. All right. So just to get us started, let's go ahead and try to write a comparator. Write a comparator for integers. Comparator for integers. All right. In ascending order. So let's do that over here for now. All right. So I want to write a comparator that takes 2 integers and then compares them, and 10 will come before 20. If we're going given 5 and 1, these are out of order, so we'll return something negative, right? If 1 is equal to 1, then we'll return positive. So int compare int, right? Compare integers, right? Should I take two integers, int a, int b, right? And then of course I could just say if a is less than b, then return -1. Right? Otherwise, else if a is greater than b, then they're out of order, so I should return +1, but we don't write positive there, right? You can, but you don't. Else, what's the only other possibility here? 0, return 0, well, because they're equal. Right? Now, is that a comparator? Let's go back to our notes here. It's only a comparator if it has this signature. Ours does indeed return an integer, but does it take two const void pointers? Nope. That's something, but it ain't a comparator. Okay? So let's go ahead and change this so that it's const int star. Now we're taking pointers, right? And we're making it const, and we're making a promise that it won't be changed. Is that a comparator? Careful. Does it still match that yet or not? Nope. These are void pointers. This is something, but it ain't a comparator. What is it? It's something that takes two integers. It's still too specific, right? We want to make this as generic as possible. Two void pointers. Void pointer. Okay? Now, the first step in here is to cast them so that we can compare them, right? Can I compare it like this? What is this doing right now? This will actually compile, probably with warnings, hopefully with warnings, because what is it doing? It's saying, is the memory location of this first thing lower than the memory location of this thing? Does that have any relationship to what values are stored in those memory locations? No, 10, 20, 5, 20, all right? It doesn't matter, the values are meaningless. But if you want to compare memory addresses, go ahead. You'll just get nonsense values, right? So how can I take memory locations and then get the elements in those memory locations? Dereference them. That still doesn't get me where I want to be. Because if you have a const void pointer, what is it pointing to? Is it pointing to an integer with 4 bytes? Is it pointing to a double with 8 bytes? Is it pointing to an airport with 50 bytes? Right? We don't know. There is no way that we can still compare these two without knowing what types they are. So my first step is to get them into a form that I can work with. I want const void or int pointers, right? X and const int y, right? Those I can work with because I know that they're integers. And integers are 4 bytes, 4 bytes. I know how to compare these 4 bytes and 4 bytes using less than, greater than, equals, equals. Right? If they were airports, I know how to work with those because I've got that structure defined, or a book, right? Et cetera, et cetera. So how do I make A, which is a const void pointer, become X, which is a const int pointer? I just force it to be const int star A, right? Const int star B. Oops, there we go. What am I doing in front? This should be familiar to everyone at this point. If I had an integer and I wanted to force it to become a double for the purposes of division, that's a typecast. I am forcing that generic pointer that can point to anything to suddenly point to these 4 bytes right here that represents an integer. You do this all the time when you call malloc without thinking about it now, right? Malloc returns a generic void pointer that can point to any memory location, whatever, right? I want you to force you to point to an array of integer elements which are all 4 bytes, okay? So now I can work with X and Y. Dereference X, dereference Y. That gives me the values stored in those memory locations. And I can ask questions about it, right? Is the value stored in X strictly less than the value stored in Y? Likewise here. Is the value stored in X strictly greater than the value stored in Y? Right? Why don't I have to have an else if condition here? What's the only other possibility? That they're equal. Right? So just else. There's a comparator for integers, right, that orders them in ascending order. Right? Imagine that 10 were stored in A and 20 were stored in B. What would it return? 10 is less than 20, so it would return something negative. They are in order. What if I gave it 20 and 10? Right? Sorry, there we go. This is not true, but now this is. Right? And so it would return something positive, saying that these are out of order. They need to be flipped if you wanted to sort them, for example. Right? What if I gave it 10 and 10? Of course, then it would return 0. Okay. Now that I've got this comparator, I can start making appropriate changes to this function here to make it generic. Right? So this to do, make this super generic. Right? It should be able to take any array, integers, doubles, books, etc. Right? So let's work on that now. Okay? Now that I've got my comparator. So const int star, this is an array of integers. How do I make it generic so that it's an array of anything? That's an array of books. That's an array of doubles. An array of anything is void. Right? I still need to know the size. In fact, I'm going to rename this number of elements. Right? There we go. And change that down here. Because I'm going to have some other things that might be confusing if I don't name these things properly. And there's the key. Okay? So for each element, if this is the thing that you're looking for, then return the index at which you found it. If that's not the thing, if you don't find it, then return -1. All right. I don't have that anymore. Instead, I need a comparator. Why? That assumed that they were numbers, doubles or integers or something like that. Is that how we do string comparisons? It's always wanting to put in a period here. Nope. What would I do for string comparisons? strcmp of the array and the key, and if that's equal to 0, then you know that they match. Right? If it were books, what would I do? I would do it like by title. I would do the first book, get its title, string comparison to the second book's title. Right? What I do here now is use this comparator that I wrote. Right? I'm going to call it CMP though. Right? I'm going to give it 2 elements, A and B. And if that's equal to 0, then I know that A and B are equal. Right? And I found what I'm looking for. Return the index at which you found it. Okay? I don't have a CMP here, and I don't have A and B. So what are my A and B? Well, my A is going to be the array's ith element, right? There's still some work here to be done. My B is going to be the key. Now be careful. What about this key? It's only an integer. So if I gave you an array of books, right, could you compare a book to an integer? No, they have to be the same type. So let's take that away. I want to make this key generic now. How do I make it generic? Void, right? You can't do that with a variable in C. Instead, you need to do it with a pointer. Only pointers can do that. Right? Am I going to be making changes to that key? Nope, so let's make it const 2. Right? Now I can pass in this key, which is a const void pointer. Guess what? It expects a const void pointer. Good. What about this thing right here? Is that a pointer? So remember this exercise that we did last time. Right? Array is a void star. In other words, a pointer. Right? If you look at a specific one, ARR sub I, I, is a single element. Right? In other words, a void, a book, or an int, or a double. Right? But CMP, this comparator right here, it expects a const void star. So I go from a pointer to a regular old variable back to a pointer. How? ARR sub I, something in front of it, fill in the blanks here for me, is a pointer to that one element. Fill in that blank. Ampersand. Good. Right. Now that's a const void pointer. Okay. All right. We're 60% there. Okay. Where is the CMP, this comparator? Well, I want to use that comparator because down here I've got an array of integers. Right? How do I get it into the function? And this is another new concept here. All right. I need to look up the exact syntax. Sorry. Darn it. Const void. Sorry. Yeah. Okay, there we go. All right. Int star CMP and then const void star A const void star. Actually, I don't need A there. I'll just do it like this. Now, did I get enough parentheses there? That's that parenthesis. That's parenthesis. Good. All right. Now I'm getting too many parameters here, so let me go ahead and stack them one on top of the other. There we go. There we go. And there we go. So I've got 1, 2, 3, 4 parameters here. What the heck is this doing right here? All right. We won't get into the details just yet, but I'll tell you what this is. Well, you can probably figure out what it is. Star. What is a star? That's a pointer. What is this thing right here? CMP. It's a function. So it's a pointer to a function. Right? That's new. But it shouldn't be that surprising. So we've got a regular old integer here. What if I did ampersand key? Right? That integer is stored somewhere in memory, right? The ampersand gives you the memory location of that variable. Right? Well, what else is stored in memory? Everything. Everything is stored in memory. Main is stored in memory. Search, the function search is stored in memory. The code for my comparator is stored somewhere in memory. Right? So it makes sense that you should be able to have a pointer to main. Right? In fact, you don't even need the ampersand. The ampersand is optional. Why? Because just like arrays, the array name itself is a pointer. A function name itself is a pointer to itself. Right? So you might have had some problems before, like doing something like the following. Double y is equal to square root. There we go. So in the very, very beginning, maybe somebody did something like this. It compiled with a warning, but it compiled and it ran. Obviously, what's wrong here? I never gave this input, right? So why would it compile? Because sqrt is valid. What is it? It's a pointer to the square root function wherever it's located in memory, right? Because everything is located in memory. So what is this doing up here? It's passing a function to another function. Because hey, search function, I want you to compare these elements and find the one that I'm looking for, the needle in the haystack. And here's the function that you can use to determine that. Okay, great. Now that I've got that function, I can go ahead and call it. Right? That makes it configurable. On one call to search, I can pass in this comparator. On a different call to search, I can pass in a different comparator for books. On a different call, I can pass in yet another comparator for doubles. That allows me to have one search function. Okay? We're almost there. Let's go ahead and try to compile this now. Right. Okay, good. Warning, dereferencing of a void pointer here. Right. Well, first of all, let's take care of everything down here. How are we going to call this now? The array, what else does it take? The number of elements, the key, and then the comparator that you want to use. So n, there are 9 elements in this array that I'm searching. The key that I'm searching for has a value of 2 here, and I need to pass that in, but I need to pass it in by reference key. Right? Why? Because we expect a pointer. Right? And then finally, here's the comparator that I want you to use. Compare int. Right? I don't call it. Putting parentheses there would mean, hey, there's this function, call that function, run the code in that function. Without the parentheses, it's saying, here is the memory address of this function, pass it to that function so that that function can call the function. Right? Now we're getting into an area called metaprogramming, right? Programming about programs, because what you could do is you could actually go to the memory location of that function and actually change what's in that memory location. Right? You could write a program to reprogram itself this way. Right? But we're not going to do that. Right? All right, so let's find out what remains here. Only that one thing there. So what is it complaining about on line 37? Right? Well, what it's complaining about is I don't know which one is the ith one. Right? So let's write some notes here. ARR is a memory address. Dot, dot, dot. A memory address to what? Right? So it's generic, right? Is it a memory address to integers? Doubles? Right? Books? We do not know. Right? Consequently, it doesn't know where the first, second, etc. In other words, the ith elements are in memory. Right? We don't know where they are, or at least using this syntax. At this point, let's understand, we've already covered arrays, but now let's go back to arrays and let's understand how they actually work using what's called pointer arithmetic. So here's the ultimate answer of why we start our indexing at 0. Here's an array, say, of integers. Now, how many bytes does an integer take? 4, or better answer would be size of int. Okay? When you have an array like this, an array is a memory address. ARR is just some random memory address where it begins. Right? So where is that first element? Well, it's right there. ARR plus 0 offset. These are indices, 0, 1, 2, 3, 4, just like I've got over here. What happens is it expands it into this arithmetic. This is the compiler doing all the work for you. Right? That we're going to have 0 bytes times the number of bytes for each integer away from the initial memory address. In other words, right here, right at the beginning, that first element. Right? Well, where's the second element? It's at index 1. That means it's this memory location plus 1 times 4 bytes away. In other words, right here. There's the second one. Third one, fourth one, fifth one. In other words, it's the index is an offset. I want you to go 4 bytes away, 8 bytes away, 12 bytes away, 16 bytes away, right? Until it gets to that memory location right there. This works because it's an integer and the compiler knows about it. This doesn't work because we don't know what they are, and so therefore the compiler doesn't know about it. Right? What would this look like, by the way, if it were doubles instead? Right? Size of int becomes what? Instead of 4, it becomes 8, because that's what double means. It's double the size. And so it would be array plus 0, array plus 8, array plus 16, 24, 32, etc. It only knows that because it's built into the language, the double, right? So the problem here is that we're going to have to do all that math ourselves, okay? So we need to come up with a memory address, okay? Const void star mem address, all right? And we're going to do that by using this expression right here, right? There's the array we're given, right? So it's array plus I times the number of bytes that the stuff takes. Right? There we go. There's my variable name. Now normally this would be filled in by size of int, but it's not always going to be an integer. Sometimes it's a double, sometimes it's a book. So likewise, we can't use size of double. We can't use size of book. So in other words, we're going to have to be told this. Number of bytes each one takes. That is yet another argument. I'll just make it an integer for now. Number of bytes each element takes. I don't want to write all that out. Right? Number of bytes each. Let's say it like that. So let me go ahead and change this variable name, to that variable name. There's my memory address. Right? And now I can compare whatever is stored in that memory address to whatever is stored in that memory address. When it gets passed off to this comparator right here, it doesn't need to know how big each one is because it's assuming already that it's 4 bytes. It's forcing it to become an integer. Right? So now let's try to compile this and see if it works. Right? Makes an integer, oh, did I screw that up? Oh, now that I'm doing this, I need to add it down here, sorry. All right. So before the key, how many bytes does an integer take? 4? Should I hard code it like that though? No, what should I do? Size of int. There we go. GCC. All right. Now, remember, I'm searching for 2. I would expect it at 0, 1, 2, 3, index 3, if it works. Haha, cool. Let's continue to test. What if it's element 10? That's our index. There are 9 elements in there, so the last one would be index 8. Hey, cool. What if I wanted to search for 1? Oops, there we go. That's going to be at index 0. It works. What else should I test here, just to make sure? Something that doesn't exist. Say 42. Now, if it doesn't exist, what should it return? -1. Hey, all right, cool. Now, to show you the utility of this, I want to now search an array of doubles. So double, burr. Right? I'll just put it as 0.1, 0.6, 0.7, 0.4, 0.3, 0.6. I'm just making up numbers here, it doesn't matter. 0.3, 0.1, and 0.1. Right? And suppose that my key D is equal to, let's search for 2.4. Okay? Let's copy this and change it. I found %F key D at whatever index. Right? Don't redeclare that. But now I can pass in burr. There's still n of them. How big is it now, though? They're double, so not integers, so double. My key D is a double. Uh-oh. Can I use a comparator for integers here? No. This is definitely a successful search, right? Let's find out what happens. 2.4 at index 0, 1, 2, 3. Oh, darn it. It still worked. Why? Because of truncation. Let's go ahead and let's suppose that it was 2. There. That should result in a at index 0. Okay, so ignore that first one. We just got stupid lucky, right? This one is definitely wrong. Why? Is that 2.2? Definitely not. Right? So why? Because we used the wrong comparator. What it's actually doing here is it's taking these 8 bytes that's stored in each, and it is forcing it to become 4 bytes. In other words, it's throwing half of it away to make its comparison. 8 bytes over here, 8 bytes over here, and then it throws away half the information. You're not going to get the expected results. So let's go ahead and write a comparator for doubles. Yeah, I am going to have to put in the work to do a comparator for doubles, but I didn't have to put in the work to repeat this entire function here. Right? What's it going to look like? Double, 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 and double. And then change the name to double. Right? But otherwise, everything else is the same. Right? GCC. And now we should get, there we go. Found 2.2, it doesn't exist, so at -1. Let's try 2.4 again. And that should be 3. Right? There we go. Yep. Right. But the point is, I only had to write this one function. And I've got this problem solved for the rest of my life. If you introduce a new type, airport, bank account, person, student, what else was there? Author, right? Then all you have to do is write your own comparator. You don't have to rewrite the same function over and over and over again. Right? You just have to write a new comparator for it. And by the way, what if I am searching for books? Let's go ahead and do one for books. Right. Compare book. Right. When are 2 books equal? You tell me. Let's get rid of all this. How do I know that book X and book Y are the same book or different books, or this book goes before this book? Right? How would you search for a book? Author. So author's last name and first name. What's another option? Title. Right? What's another option? Date. Another option? Rating. Right? ISBN. Right? The options are endless. What if you wanted to sort all these books, the best books to the worst books, or reverse that, right? What if you wanted to sort it by author's last name and first name, or reverse that, or any of those other pieces of data that I mentioned, but then also reversed? You would be copying and pasting a lot of code. Whereas you only need one comparator and one sorting function or one searching function to get the job done. So let's do the title since that's easy. Right? If, okay, actually no. X's title and Y's title. Why did I use the arrow operator, by the way? I've got what to the book? A pointer. When you got a pointer to a structure, what do? The arrow operator. Right? How do I compare those? They're strings, right? Do I have something already that compares strings and follows the same exact pattern that I'm expecting? Yep, str CMP. Don't reinvent the wheel. Right? You've already got that. Just use it. Since it's that simple, what would it look like if we did it by author? In fact, let's go by title there. By title. What would by author look like? Well, we need to make sure that they've got the same last name, right? So let's order them by last name. So int x is equal to strcmp, x's author, I think we did it like this, dot last name. So let's look at our definition again. Here's the book. We've got a pointer to it. I get the author, but the author is just a regular old structure. So how do I get their last name? Just the dot operator. And then Y's author's last name. There we go. Should I just return that immediately? I could, right? But what if I have two authors here? In fact, there was two exact same authors. Who was it? A book that I'm going to start reading. Stephen Wright. There we go. Stephen Wright is a comedian, old school dry comedian, and he just released a book. And when I was searching through it, I was trying to find the book, I actually found another book by Stephen Wright. Right? Exact same author, but it was like some political thriller. So I put them both on my list thinking, wow, that comedian, he wrote a political thriller too? What? And then later on I found out that there are two people named Stephen Wright that are both authors, right? And so I threw the other one away. I didn't want it, right? So what if we have many people that are named Wright or Smith, right? How do we break that tie? First of all, how do I know that they have the same last name? What value will x have? X is 0, right? Then they have the same last name. So look at the, I could, but before I do that, then do what? First name, right? X is equal to strcmp of the exact same thing, but the first name, right? There. Now, if that's all I have to go on, then I'm done, right? But obviously I looked it up, and actually I looked at their picture and I knew, oh, that's not Stephen Wright. Primarily because he was way too young, right? So how would you break ties then? So if x is still 0, that means we have the same first name and the same last name. How do we break ties now? Date of birth, right? Maybe they were born on the same day. So we've got two people named Stephen Wright born on the exact same day. Now what do? Ultimately, what we do is we introduce what's called a surrogate key. A surrogate key or a natural key. For example, how are people uniquely identified in the United States? Social Security number. Right? How are books uniquely identified? ISBN. How are media uniquely identified? Like movies and such. I think it's EIDR, something like that. Or whatever, right? There's always some sort of natural key that is automatically generated but guaranteed to be unique to something, right? And that's what you would do in the end if you needed to, right? But this is good enough. At the end, I'll return x. Okay. All right. We'll look at this in practice when we actually have something to sort. But otherwise, let's continue, right? That's all good. That's all good, right? So, okay, yeah. So we wrote our own searching algorithm. Don't do that, right? So searching in C, use the built-in search library, right? So there is a search library, guess what it's called? Search.h, right? And there is a function called lfind, right? So let me check it out. Lfind. Can I find it? Nope. Okay, so we're gonna have to look it up. Actually, let's just do it over here. And lfind. Right? So L stands for linear search and append. There is another L search that searches then appends. That's not the one that we're going to be looking at here. So let's go ahead and grab this and talk about it. Right? So it has the following signature. Yeah, it's big enough that let me do this. See, there we go. Okay, lfind, and let me make it prettier. All right. Hey, a lot of this is really, really familiar, right? So, what is the first one? Key is a pointer to the key value you are searching for, right? We had a key, right? And we also passed it by const void star, okay? Base is the array you want to search. And again, both of these are const void stars, okay? NELP is actually number of elements, number L. Let me rewrite it like that now because that's the usual way of doing it. Nel is the number of elements. In other words, the size of the array. Right? That's also familiar. Right? The width is the number of bytes each element takes. And again, why do we need that? It's because of how pointer arithmetic works. We basically just rewrote the lfind function from scratch, right? But why write it and do it yourself when you can just bring it in and use it? Right? And that's what we'll do here in a second. We'll replace our code even further. And then finally, compare is the comparator function you want to use to compare. Right? And again, it follows that same pattern. Return something negative, positive, or zero, depending on the relative ordering of things. However, something that is completely different from our implementation is the return type. What is the return type? Is it an integer that tells you the index at which it found? Nope. What is it? It's a pointer. It is a pointer to the first element that matches your search criteria. Right? Not the index. Right? So what do you think happens? If successful, a valid pointer is returned. And you can use it. If unsuccessful, what do you think happens? Null. It returns null. The only thing that it can return. Okay? So, with our remaining 7 minutes here, let's throw away our entire implementation and just use lfind. Right? So, for the first one, int star found is equal to, what was it called? lfind. And by the way, I need to bring it in now. So let's go all the way to the top here, and I need to include the search library now. Okay? lfind, and what are my arguments? The key, the array, the number of elements, and the width. So the key here is going to be my key. The array, I'll search ARR. N, size of int. In other words, it's pretty much the same that I had up here, just a little bit slightly different ordering. Okay? That's the width, and then finally the comparator that you want to use to compare. And in this case, it was compare int. There. Likewise, if I wanted to do it for BR, what would it look like? Found A and B. There we go. Not the key, well, the key D, BR, still N things, but now it's a double and a compare double. Okay? Let's make some checks here. If found A is not equal to null, then I will print it out. Printf found %d at, now I don't know what index it is, but at memory location, %p with a value of %d. Right? So I'm searching for the key. I got back found A, and then dereferencing found A will get the value stored in that memory location. Okay? So once again, that's the thing I'm searching for. That's the memory address that you found it at because it's not null. And dereferencing it actually gives me what's stored in that memory location. Else, if it is null, then printf unable to find %d end line the key. Right? Same exact thing for the second one. Oh, sorry, this is a double. Right? Found B. Found %f at memory location P with a value of %f. And that's found B, key D, and found B. Otherwise, I'm not able to find key D, which is a double. Right. I'm going to go ahead and get rid of, well, no, I'll just leave out that stuff. Is that good? Let's find out. GCC. Okay, darn it. Bur N. Oh, sorry. The array. I never passed in the array, did I? No, I did. So, key, array, number of elements, width, and comparator. Yep, that should be good. Yeah, all right, fine. Forget about... Oh, no. It's not compiling because I don't know anything about books. So, what should I do? Include the book library that we already wrote. All right. Now it should just be warnings, right? Oh, nope. Come on. Line 58. What was wrong? All right, X is a book. Author. What's wrong? Oh, duh. Can I use that X right there? I've already got a book called X. Can I use that variable again for an integer X? No. R for result. R, and R. Probably have to do the same. Is that the only one that I had? Yeah, okay. GCC. Okay, just warnings now. Hopefully it works. Ah, darn it. Segmentation faults. Right. So, let's explore this. Actually, should I just leave it and we'll have an opportunity to do GDB next time? As a review of GDB or not? Okay. Or can I find it really quick? ARR n size of int, compare int, key D, bur n size of. It's not these, I'm pretty sure. I'll find. Array, size of the array. I'm not seeing it. So we'll have to debug this next time. Or if it comes to me, then I'll say what was wrong next time before I post this code. Okay. All right. Any questions? The takeaway today is you've got these things called comparators, so that you don't have to rewrite code. You can write generic code.